I have been searching for AWS Cloud Architecture videos, but the majority of videos I found were mainly speaking of each individual services like EC2, S3, etc. I didn't find videos creating a complete architecture containing various services. So I thought to myself, maybe this is a chance to surprise the YouTube algorithm. For the video to be exciting, I thought of creating a real-world architecture. Those type of videos are presented in the AWS series. This is my architect. AWS series, this is my architect, has invited Lancome Technology to talk about the architecture of one of its customers. The architecture is a scalable video conferencing tool for an insurance company. Before we start, you should watch the video to grasp the architectural general idea. To summarize, the happy customers calls the insurance company, asking for a meeting. And after that, the agent starts a session on their website. Both the agent and the customer join the session. Now, after the customer finishes telling his jokes, the meeting ends and the recorded video gets uploaded to a storage service. Finally, the private service gets notified to start converting the recording file and upload it back. First, I want to tell you something. The diagram that was showing is missing. Yeah, the underlying infrastructure like VPC, subnet, route tables weren't presented in the video. As we start creating those services, we need to ask ourselves a few questions to conclude what the architecture will be. The question are, do we have a public services? Yes. The EC2 instance where the Open Video platform resides need to be publicly accessible. Do we have a private services? Yes. The ECS where we are going to host the converter service doesn't need to be publicly accessible. Finally, do the private service need to access the public internet? Yes. ECS services need to access other AWS services like S3, SQS, and CloudWatch. I will use CloudFormation to create the architecture, as it provides a safe rollback mechanism. And you, don't ask me why I didn't choose Pulumi or Terraform. It's because I don't like it. So let the construction begin. Based on the responses, the underlying infrastructure will contain VPC. The enable DNS support and enable DNS hostnames properties are helpful in discovering the services under the VPC by DNS name. Public subnet for hosting EC2. We create two subnets on two different availability zones as it's a best practice. Private subnet to host private services. Internet gateway for allowing public subnet to be publicly accessible. Net gateways give private subnet the ability to access other AWS services or the outside world. We define two IP addresses and attach them in the public subnets. Route tables for the public subnets to route traffic to the internet gateway and receive traffic in, and net gateway for private subnets to allow them to talk to the public world. Finally, we create an output block to export resources. We will need this for future stacks. Now, to create the CloudFormation resources, we use the AWS CLI, passing the stack name, the template file, and capabilities to allow CloudFormation to create YAML roles on our behalf. And finally, the environment name. You can find the code link in the description. Now, let's move to the console and see the static status. Here is the create in progress status. We should wait until the stack status turns into create complete. Here is the complicated version of the underlying infrastructures. But yeah, don't worry, here is the simple one. Open Video documentation provides a comprehensive guide on how to install the platform on EC2. If you visit the documentation and go to deployment, Open Video AWS, we can see it provides a CloudFormation file. We download the file and open it with VS Code. For our testing case, I refactored the file to create resources under our VPC, not the default VPC, and remove the unnecessary resources like elastic IP address and a few parameters. You can find the new file link in the description. Let's start understanding the refactored code. The first block is the parameters, which contain the wish cert. As we run a test environment, we don't need to generate a TLS certificate. So we set the value to self-assigned. OpenVideo secret is the password we'll use to log into our OpenVideo platform. Instance type is the EC2 instance type. The default is C5 large, C5X large, which is a 4 vCPU and 8 GB of RAM. But you can choose whatever you want, of course. The second block is resources, which contains the EC2 instance and a few other resources. To deploy application on EC2 using CloudFormation, they have declared CFN init. Alongside that, CFN init needs AWS CloudFormation init for declaring scripting files. Like this file, shake app ready, will ping in a loop, checking for the health status of the app. This file also for adding OpenVideo environment variables. Some of the other resources is Lambda function to copy OpenVideo AMI to the current region that get invoked OpenEC2 creation with custom resource. That's logical, as the AMI should exist in the same region you declaring the resources. Lambda role to allow copying the AMI. Security group to allow public access. The last block is outputs, where we are going to display EC2 public DNS name and IP address. Let's deploy the resources, create a stack passing the capabilities, and the OpenVideo secret, of course. We check the stack status. Here is create in progress. Wait a few minutes, and here is the create complete status. We create a session and try to join it. All things look good, but when I try to press record, it doesn't work. This is the default behavior of OpenVideo, as OpenVideo recording environment variable is false. So the next step is to enable the recording feature and copy the recording to S3 bucket. Browsing the recording section on OpenVideo documentation, we can see to enable the recording feature, we just change OpenVideo recording environment to true. Now, if you scroll down, you can notice the uploading to S3 feature is limited to OpenVideo Pro. And we are using the community edition, so we need to create our own uploading to S3 feature. We will use the Z command to update the environment variables inside the .env file. Because the update to files will not get affected, we need to delete the stack and create it again. First, let's understand the recording behavior. We will create a session and start recording. When we create the SSH key, with CloudFormation, the key value get uploaded to SSM parameter store. So let's download it. Then we SSH into the server and watch the directory /recordings, where the OpenVideo stores the recordings. The moment we click on the record button, a folder gets created with a JSON file starting with .recording. The .recording JSON file contains a status key that has the value started when the recording starts. Let's try to stop the recording and see the status new value. Here it changed already. So we should test for a period of time on each folder created on /recording if there is a recording file. parse the JSON and check if the status equal to ready. Then upload files on the same directory to S3. Good. We get the logic. Now let's try to write it on Python. First, we define the recording bucket. Be sure you pass a unique name across AWS. We define the path to the recording files. Then list each folder under that path and search for the file that starts with .recording under each folder. If the file exists, we load it with the JSON library and read its status. If the status is ready, then we upload the file that ends with .mp4 to the recording bucket, which references the recording bucket resource name. We install the boto3 package, which our script used to communicate with AWS. And to run the script periodically, we create a cron tab every 1 minute inside the user data. Let's delete and create again. Now logically thinking, if we record and stop, the cron tab should pick up the video and upload it to the bucket. We console the S3 bucket and see no videos. Let's SSH into the server and run the script by ourselves. Oh, we get an error. The bucket name was missing a double quote. Let's fix it. We nano into the file and add the double quote. Rerun the script and we see another error. Unable to locate the credentials. Can you find the solution? Well, it's the time to win the $1 million.
A はい、こうファイナルアンサー。
はい、ファイナルアンサーでございます。
ではこの750万には帰れません。
結構でございます。さよなら。ね。
Yes, you are right. AM role was missing to upload the files. Let's add an AM role and assign the desired policy. This AM allows all S3 actions on the recording bucket resource. Then we create an instance profile and pass the AM role. Try it again, record, stop, check the bucket for the video, and here is it. We get a successful upload. To help to intercept and send events, we need to welcome Event Bridge. Event Bridge can save much time writing hard and spaghetti lambda function code that intercept events from a source like S3 and redirects them to a target like SQS. But why we choose SQS to pass the event to and not pass it directly to SES? The first reason, SQS decouples the file uploading feature from the processing feature, allowing handling spikes in traffic. Second, messages are stored in a queue until they are processed successfully. And finally, SQS adds visibility to the process, like how much messages were received successfully or unsuccessfully. Let's start creating the resources. First, we need an SQS resource, the visibility timeout property explaining the time the message is untouchable after pulled for processing. We set it to 6 minutes, as the SES tasks, the puller, will not exceed 6 minutes processing the file. Add a drive policy for directing the unsuccessful pulled events to a dead letter queue for further debugging. And max received count is the number of retries before redirecting to the dead queue. We create the dead letter queue. Next is creating the event rule to intercept every object created event from the source S3 with the name recording bucket. As the bucket resource is defined in another stack, we use the import function to get the bucket name value. Then we define targets property to tell EventBridge where to redirect those events. In our case, the target is SQS resource. To forward it to the created queue, EventBridge by default has no permission to send messages to SQS. That's why we need to create a queue policy to allow sending and receiving the messages. For the outputs, we export the queue name, ARN, and URL for further use on the next stacks. Also, the recording bucket outputs weren't defined in the previous stack. Let's export the bucket and update the stack. After we create the EventBridge stack, the stack status becomes rollback complete. That's because we have a CloudFormation syntax error. So let's fix it. It seems the import function was wrongly defined. We start by creating the stack again. Then open the source S3 bucket to upload the file, and SQS to watch for messages. Let's upload the file and watch the SQS. No messages were received. That's because we need to tell our recording bucket to send events to EventBridge. So we go to the previous stack and update the recording bucket resource with the following changes. Re-upload again, and here is one message that has been received. As we finish setting up EventBridge and SQS, let's move into creating the ECS tasks. To convert the recording into HLS file, we need to create a script that incorporates several steps. First, we pull the messages from SQS. Next, we obtain the bucket and file name associated with the recording. We then retrieve the recording from S3 and utilize FFmpeg to convert it to HLS format. Finally, we upload the converted file to another bucket. If the entire process runs successfully, we delete the message from SQS. However, if the process encounters failures, we allow for 5 tries before redirecting the messages to the queue. Let's create the destination bucket and the ACR. Initially, we open the ACR and review the push command for the image. Subsequently, we proceed with logging into the ACR and building the image. Finally, to push the image to the registry, it's crucial to tag it with the registry name. Now let's proceed to run the image locally. We will import the environment variables queue name and destination bucket name from the previous stacks and pass them to the docker run command. It's important to note that when running the script locally, you need to provide the secret key and access key. However, when deploying the secret on the ECS, EM is used as an alternative and thus credentials are not required. Since there are no messages on the queue, we will not see any outputs. To test the functionality, let's upload a sample video as a recording and observe the results. Here are the logs. It starts processing the queue messages, creating a folder, uploading the HLS files, and ultimately deleting the message from SQS to not be processed by another task. Now let's visit the bucket, and voila! We can see that our folder contains the HLS files. This confirms that the script is working fine. Can you guess what the next step is? Indeed, the next step is to upload the container to ECS. However, Docker images cannot be directly uploaded to ECS. They must be in a specific registry, such as Docker Hub or ECR. In this case, we have already utilized here. To begin, let's create the ECS for Gate. The ECS requires a cluster to exist at first, and for networking purposes, we need to define security groups and import 2 private subnets from the previous stacks. Lastly, we need to define the task definition to specify and execute the container. The task definition requires 2 roles. Execution role rn. This allows ECS to fetch the image from the registry and create logs. ECS role. This enables the container to query SQS and to put files on the destination bucket. Additionally, we pass the queue name and destination bucket name as environment variables. Since we have already pushed the Docker image to the registry, let's create a parameter to pass the image URL. Then we can proceed with creating the ECS resource. Now we can run the command AWS CloudFormation update stack to initiate the update process. Once the update is complete, we can open both the source and destination buckets. Upload the video. And navigate to ECS to check the container logs. We select the stack and proceed to the logs section. And there is it. The file gets processed and uploaded as HLS files to the destination bucket. Let's go ahead and check the files. Now after we get the task service running, let's suppose that SQS get that many messages that a single ECS task cannot handle. So we will need to add more tasks to keep up with the load. That's when the scalability comes. Based on the architecture, the scaling of the ECS will heavily depend on the SQS. Meaning, if the approximate number of messages visible, which refers to the number of messages on the SQS, is above a certain threshold, we scale up the ECS to consume more messages. But, like what the blog said, it's more complicated than that. The number of tasks on the ECS can be driven by multiple factors, such as how long it takes to process a message and the acceptable amount of latency, that is queue delay, service can have. Now, after we understand the scaling mechanism, we shall start curating it. Going back to the blog and taking a look at the design, it seems they have used a Lambda function to publish custom metrics to CloudWatch. But AWS has developed a new method that instead of using a Lambda, we can use CloudWatch custom metrics that adds the ability to query different metrics and use math expression between them as a result. We start by creating scalable target. While we want to increase the number of ECS tasks upon scaling, we set scalable dimension to ECS service desired count and reference the ECS service name on resource ID. Scalable target need a role to execute the scaling, so create a role and give application autoscaling the permission on our behalf on the ECS and CloudWatch resources. Next, we'll use step scaling instead of target scaling policy, as it gives the ability to add lower and upper bounds for more customizations. We define 2 policies for scaling. The first one is scale down policy, which have a name and reference the defined scaling target. Then we add scaling configuration which tells to scale down by 1 whenever the approximate number of messages visible is 0. The cooldown property is crucial here, as it tells the autoscaler to scale after 180 seconds from the previous scaling activity. This prevents accidentally scaling up or down the services. On the other side, scale up policy will take the same parameters as the scaling down, except the step adjustment configuration is different by defining the metric intervals. If approximate number of messages visible is between 10 and 25, we scale by 1. Else, if it's between 30 and 45, we scale by 2. Else, we scale by 4. Now here it comes the fun part, the CloudWatch alarms, which is in another word, the triggers. Let's start creating the first alarm, the scale down. We create an expression that returns the backlog per task, which expressed as the value of a custom metric SQS messages divided by the value of a running tasks metric, and set return data property to true as we only want this metric data. Defining SQS messages metric, the metric name is referring to approximate number of messages visible in the SQS, also passing the queue name as a dimension. For the period, the metric will be calculated every 60 seconds. The other four properties, comparison operator, evaluation periods, threshold, alarm actions, tells the alarm to wait for 5 multiplied by the period property, which equals 5 multiplied 60 equal 5 minutes, and test if all the values are less or equal to the threshold, which is 5. If yes, it triggers the scale down policy. The same for the scale up, except we change the comparison operator to greater than threshold and the alarm actions to trigger the scale up policy. We will disable the event bridge on S3 so we can upload the tasks without publishing events to SQS, and then we return it back to on. Next, I wrote a script to send messages to SQS. Each message contains an S3 file to process. We start by defining the boot3 and the clients for S3 and SQS. Then, list files under the source bucket and append file names. Looping on each name, we create a message like the S3 is supposed to send. Finally, we take each message and send them on bash to SQS. We run the script and check the SQS. Here we received the 49 messages. Now checking the alarm state. The scaling up backlog alarm will get triggered scaling the SES by 4 as the backlog is above 35. We should get an increase to tasks desired count to 4. If the message is still above the threshold 35, another increase will get triggered resulting on having 9 tasks. Last, if all the messages get consumed and we reach 0 messages, the desired count will decrease by 1 until it reaches the minimum desired count, which is 1. And by that, I can tell you managed to create a complete architecture of an insurance company using CloudFormation. I hope you like the video and don't forget to like and subscribe to the channel.